the floor is, it has this dimension. And there is going to be a force on the floor downwards due to the air pressure inside the room. I mean, the air pressure outside here, the atmospheric pressure outside, we already told you about it. It was 10 to the 5th Pascal, right? So it's 100,000 Pascal of pressure where we all live close to the sea level. So there is that much pressure that is on top of that floor. So there has to be a force on it that's pushing it down due to the atmosphere. And we can calculate the amount of that force, which is simply P of the atmosphere times the area it is applying on. So that is 1 times 10 to the 5 pascals times the area, which is 20 meters squared. Okay, pushing down. So this is 2 times 10 to the 6 newtons, right? I mean, think about it. This is a massive force. There is an enormous amount of force pushing down on the floor due to just simply atmospheric pressure around us. So you can see how much pressure, this much pressure, how much force it can induce on different areas of your body or the floor in your room. And the larger the area, the larger the force, of course. So these are examples of how you calculate force from pressure, or simply calculating weight of objects from their density, like we did for the air inside the room. Okay, any questions? I mean, that is a massive force, as you can see on the floor. And one wonders why the floor doesn't collapse. Do you know why the floor doesn't collapse? We'll get that in. We'll get there in a second. Okay. So in order to find out why that floor does not collapse, let's calculate pressure as a function of depth inside a fluid. Okay, pressure inside a fluid. Okay, let's call this one, and so this is inside any fluid, but we will only use liquids here because liquids are incompressible. Okay, as we talked about yesterday. So we said gases are compressible and liquids are not compressible, incompressible. So suppose I have a container and it holds some sort of a liquid. It can be water or whatever liquid it is, some liquid, such as water. Okay, can be anything else. All right, now if I just have this bucket of water or a liquid sitting on my desk and doesn't do anything, there is no flow in it. There is nothing moving around. The liquid is sitting standstill and doesn't do anything. It's happy. There's no flow. Nothing is moving in it. There's no fish swimming inside of it, nothing. All right? So if I just look at some block of it, if I only look at some block of this imaginary block of water inside this container, and suppose it is some, you know, it's just some imaginary block of it. Block of the liquid in there. All right? And that block, of course, is just sitting there. It doesn't float up. It doesn't go down. It doesn't move to the right or left. It's just there. And if it is there, we can say a lot of things. Let's create this coordinate system here first. Okay. All right. So let's assume the top of this block is at some y naught, and the bottom of it is at some y, just y. Okay, and that it has some surface area. That's the area of the top of that box. Okay? Now, because this box is not moving anywhere, because it's just this chunk of that liquid that I have built up in my imagination, but I know for a fact it doesn't move anywhere because the liquid, there's no flow in it, there's no swimming fish inside, this thing is just sitting there doing nothing. That means that whatever is the pressure on, whatever the force on top of it that's pushing it down, obviously there's a force on top of it pushing it down on top. And then there's also this there's a force from the bottom that's pushing up on the bottom side of this box due to the pressure at that depth. So the top pressure, the top force is due to the pressure at the top depth, and the bottom pressure, the bottom force is due to the pressure at the bottom depth. And of course, there's also the weight of this entire block, right? This entire block has a weight. Which I can just draw a free body diagram of it around its center of mass. So because this block is not moving up, is not moving down, it's not going anywhere, the sum of all these vector forces need to add up to 0, right? So I can then write down that sum of all forces has to be 0. Okay, now I can write those as W plus force on the top plus force on the bottom equals 0. Now I can write these in terms of their components in the coordinate system that I have drawn here for you. All right, so W becomes the total mass of this block times G in the y hat direction, plus the force on the top is obviously the pressure on the top times the surface area. That's in the y hat direction as well. And the bottom force is the pressure at the bottom times the surface area, but that one is in the minus y hat direction because it's pointing up and my y is going down. All right, so now I can just factor out the y hats. Okay, now that means everything in that parenthesis has to be equal to 0. So then I can write it as P at the bottom is equal to P at the top plus mg. Okay? But, all right, so now I need to find out what m of the total mass of that block, imaginary block of liquid is. And that's just simply the density of the liquid times its volume, which is A times y minus y naught. Anytime you guys get confused, please stop me and ask questions. Okay, so far, we have that equation. Now, obviously, I can cross out the areas from both sides of the equation. And then I finally get to the equation that's equal to P at the bottom is equal to P at the top plus rho of the liquid G times y minus y naught. All right, so that says, let's go back to our situation. That says, for that, if I am at y naught and y, the pressure, and then at here I have P top, and here I have P at the bottom. So the P at that level, y naught, and the P at the bottom at level y are related by this equation. All right? So now I'm going to do something to make this equation a little bit more friendly. I'm going to say, you know what? I'm going to let y naught go to 0. Means I'm going to lift it all the way up to the surface of the liquid. Okay? Then, of course, at and then at y equals 0, of course, P becomes P on the top of liquid. Okay? And then also, I'm going to let y be equal to h. All right, so now I'm going to rewrite the equation. P is equal to P on top. This is P on top of liquid plus rho of liquid GH. All right, so now I have a much better equation to deal with. It tells me that pressure at any depth h in a liquid, of course in a gravitational field, is equal to the pressure at the very top of the liquid plus this thing called rho gh. Okay? Any questions? So,
I have a quick question. Sorry.
yes,
Is the pressure at the top of the liquid the atmospheric pressure?
that's correct.
Okay, thank you.
Of course, of course. That's correct. I was just writing that right now. Okay? And then h is the depth to which you go down from the surface of. So that's just the depth now. Okay, so at this depth h, pressure is the same everywhere here. Pressure here is that equation. Okay? Now, it only depends on H. The pressure of the liquid at depth H only depends on H. All right? It means it doesn't depend on any other dimension of the container. It means, suppose I have a container that looks like this. Okay? And I have other containers that look completely different. I don't know. Maybe one of them looks like this. And it's filled with the same amount of liquid. Maybe it looks like a tube tilted, and it still has the same liquid. So it doesn't really matter what shape this thing has. At a given height, I mean at depth, at a given depth, H, pressure is always the same in all these containers. So P here is the same as P here, is the same as P here. P is only P naught plus this. That's it. It does not depend on the shape or anything else of the liquid. As long as the height is the same, that's your pressure. Okay? Now, so this thing is very useful, and people have used this equation to create clever pressure measuring devices, barometers and things like that. And one way of measuring creating a device that measures the pressure of atmosphere for you, for example. Okay, so sometimes you want to find out what the atmospheric pressure is in your room. There is a clever way using this principle to calculate a little bit indirectly what the pressure of the atmosphere is in your room or your laboratory. And the way you do it is this. So this is I think it's called a mercury manometer. Let me just make sure. Yes, wrong. Okay, so a mercury barometer is a column of mercury that measures the atmospheric pressure wherever you put it. Okay, and this is how you build one. You get a glass tube and you fill it with mercury. Filled with mercury. Then you put a glass top on top of it, a glass stop. All right, so the mercury doesn't spill out. Then you flip it. Okay, so I still have, this is still mercury in it. All right, so you flipped it. Now you're going to bring a container, and that container has mercury in it already. All right, then you're going to go and remove, then at the end, remove glass stop. right? You remove the glass top. Okay, so you're going to remove that. There. I just removed it magically. All right, so what happens as soon as you remove, the mercury is going to want to go down on the tube, but it can only go down to a certain level. And here's the reason. So it only goes down to a certain level. And this becomes the final state of the affairs with the mercury inside this tube and the container. Okay, it only goes down there. And because it goes down from having only mercury in it, there is no air in it inside this cavity. Pressure is zero because there is nothing there. No gases. Remember, this thing was full of mercury. It just came down due to the gravity, so therefore there's nothing there. So there's no pressure there. But it cannot go all the way down to the level of the rest of the container because there is atmospheric pressure here. So this level here is where the two pressures are equal. The pressure of the column of the mercury at that point is equal to the pressure of the atmosphere. So the pressure, this level, is where the two pressures are equal, meaning the mercury column is equal to P of atmosphere. And we already know what the pressure of the mercury column is. We calculated that. That is rho of mercury, G, and then H. And because there's no pressure on top of it, so I have to add it to zero, but it doesn't really matter. And that's the atmospheric pressure. So there is your equation for a simple mercury barometer. All you need to do every morning, well, if you graduate the side of the tube, you can read the height. And once you know the height of that mercury, you multiply by G and the density of mercury, which is just a constant known. You know what the atmospheric pressure is that day. And if there is a storm or it's hot or cold, the pressure, atmospheric pressure changes in your room, and every day you will read a different height and you know what the pressure is. So this is a pretty simple, the reason people don't use this outside labs is because mercury is poisonous and they don't want to get people sick. But it's a pretty nice little device that gives you the atmospheric pressure wherever you are. Okay. All right. So let me now go to the next subject. All right, there we go. Any questions, guys, so far? Everything's clear? Okay. All right. Now, let me talk about how pressure inside a fluid is transmitted. Okay, so suppose I have a container and a piston. So this is a piston. And I have a container full of some fluid. Actually, this is a incompressible fluid, which is a liquid. Okay, that means incompressible fluid. Okay. All right. Now, we all know we just did that, and at some height h, pressure is equal to pressure on top plus rho of the liquid GH. We just proved that. All right, so if on the top, then if I push down on this thing, on the piston, with some force, okay, so this is some external force. Push down on the piston, and piston wants to move down, so I can calculate the external pressure on top. So the top will then have, the top of liquid then would have my force distributed by that piston as a force, as a pressure on top of it, right? So that would be the external force divided by the cross-section area of the piston. So this is piston with cross-section area A. Okay? It has a cross-section area. Maybe I should put this arrow somewhere else. This is the cross-section area. Okay? So the pressure on, I can then change the pressure on top of the liquid by changing the amount of force that I'm applying on top of that piston. Okay? So then I can write this equation as P at any height h is equal to rho of the liquid GH plus P on top, which is my external force divided by the piston's area. Okay? Now, this force, this pressure at height h, this is now you can see this is a function of h. The pressure is a function of h, so it depends on where h is. But for a given h, the pressure will show up everywhere on that liquid at height h, and it doesn't matter. The pressure shows up at, so the pressure at this height shows up on the walls this way, it shows up at any point here, and shows up at this wall that way as well. So as long as you're at that height h, the pressure shows up equally everywhere within that liquid at height h, and then also at height h, the pressure is transmitted to the walls of the container. So that brings us to what we call Pascal's principle. Okay, which is what? Which is a change in P, a change in pressure applied to an enclosed incompressible fluid shows up everywhere. Within the fluid and walls of the, actually, walls of its container. Okay, so that pressure shows up everywhere at that height, at that depth, I mean, everywhere in that depth H, within the liquid or the incompressible fluid, which is the liquid in this case, and also on the walls at those points, at those heights of the container. Okay, this is called Pascal's principle. It's sort of obvious, but somehow Pascal's name's attached to this thing. Okay, so we can actually use this thing to do real, to build real devices that do a lot of heavy duty work for us. Okay, so let me give you an example. Suppose I connect two of these devices, but they have two different, so here's my piston here. Okay, so the piston's here with cross-section area small, and I have another piston here with the cross-section area large. So this is the cross-section area here, and this is the cross-section area here. Okay, now I'm going to put a external force here. I'm going to call that input. Okay, so I'll just push that small piston, and of course, you know, there is a fluid, there is a liquid here. Okay, so I'm going to push down on that small piston on the small end, and obviously there would be a force on the output pushing the other piston up. This is obvious. So now we want to find out a relationship between these two forces. Well, that's not that difficult, because we just said if we had the same height here, I can calculate the pressure on everywhere on this liquid as long as I'm at the same depth. So these two are the same depth for now. And I can then calculate the pressure at the input. So the pressure at the input is equal to force that I'm applying divided by the area of that piston, right? So that's the pressure here. Of course, that pressure will then be transmitted due to Pascal's principle all the way into the liquid everywhere and shows up at the other piston, right? So the piston, the pressure at the output which has to be equal to the pressure, which is, you know, it's the force output over A of large. This has to be equal to pressure of the input, right? By Pascal's principle. All right, so the pressures have to be equal because the pressure shows up everywhere in the liquid. And as long as they're at the same height, it's exactly the same pressure. So we're at the same height, so those are at the same pressure. All right, so now I can go ahead and rewrite this equation as F out over A sub L is equal to Fn over A sub S. Okay, so then F out is equal to Fn times A of the large over A of the small. So look at this. Because, so you can see that because the area of the small piston is obviously less than the area of the large piston, because of that, F of the output has to be larger than F of the input. This is how you can actually use liquids to do all the really heavy duty work for you by pushing down on the small end a little bit and getting a large force on the other end. Okay, this is how hydraulics works when huge huge demolishing machines start destroying buildings or huge earth moving tractors do their work. It's usually pushing down with a small force through some oil-filled containers and getting a much larger force at the other end that does the work for you. Okay. All right. So this is how you can use the Pascal's principle to your advantage and do a huge. This is really a force amplifier if you think about it. It amplifies the amount of force you put on one end through this clever Pascal's principle. All right. Any questions so far? All right. All right, so let me change gears. All right, so let's go back to the container of fluid or liquid. It doesn't really matter. All right. And you always have to remember we are in a gravitational field. When you see the surface of the water like that in the container, that means you're in the gravitational field. Otherwise, the water would not even go into the container to begin with. All right. So you have a container full of some liquid. Suppose it's a liquid. Now you're going to submerge. So let's submerge some object, maybe a piece of rock or something. So let's submerge an object like that. It just looks weird, but I just submerged it. Now, remember the pressure of a liquid depends only on the depth. So if you think about it, this depth is pretty small, and this depth is this is the largest depth. And then you have these other depths in other places. I mean, this is some medium depth and stuff. So the pressure obviously gets larger and larger on the deeper ends of this object, and the pressure is smaller on the upper ends of this object. Okay, so if I were to calculate local pressure, if I use this little area and find the pressure here would be small, I mean, force here would be small because it's just pressure at this height, small, times the area, that little area that I've chosen. So you can see the pressure is pretty small on these top ends. Not pressure, I mean forces. The little tiny forces are small, but as you get down at the bottom, these forces get larger and larger. Right? And then they're medium because the height is medium. And then they get smaller and smaller again. So they get larger and larger as you go deeper and deeper. Right? So the net result is, then if I added all these vectors vectorially, I would get some force, let's say this is center of mass of the object, I would get some net force pushing it up. This is some net force. Net due to the pressure. Whoops. What the? Okay, so there's a net force pushing it up. But at the same time, because this is done on the object, the center of mass, there is another force, that's the weight of the object itself. Right? The weight of the object wants to pull the object down, and this weird force that is induced by the pressure of the liquid wants to push it up. So that the net result is the apparent weight is equal to, the force, real weight of the object minus the buoyant force. Okay? So this is the apparent weight of an object submerged inside a fluid, now in this case a liquid. All right, so you can see, obviously, you've experienced this thing, when you go swimming in a pool, an object inside the pool submerged weighs less. In fact, if you have a ball, a basketball, it doesn't even get submerged because the buoyant force is just so huge, it does not let the ball go down at all. On the other hand, a piece of rock, goes right down to the bottom of the pool. And there are other objects that kind of float in the middle of the water without going down or up. So that's this buoyant force that's acting on the actual real weight of the object. And depending on the size of it, the object could either sink all the way down or float all the way up or just completely float in the middle. We're going to talk about this and find out how to calculate this buoyant force. So we can go ahead and calculate the apparent weight of an object submerged in an external fluid. We are all in an external fluid. This is the atmosphere of air that's around us, and our weights really, when we weigh ourselves, really are not the actual weights with nothing else on. It's this apparent weight because there is this a little bit of buoyant force on us due to the air that is around us. But in a liquid cup of water or a pool, those forces are much, much larger, and I'll explain why they're larger and how to calculate them. Okay? We may be running out of time here, so I may stop because this is gonna take a while. So why don't I stop here? Give me a second. Let me get a screenshot. All right. So I will continue tomorrow and explain how to calculate this buoyant force. All right.